today we're going to talk about a panorama of results from the THyGA project, which started over 3 years ago with a kickoff in Brussels. So we're happy to close the loop today with this final workshop. So I will do just a short introduction and rules to this event. Then we will have a presentation of the THyGA objectives and organization of the project, what we aim to achieve by our project coordinator, Patrick Milan. Chris David will present the work package 4 and the work on certification of new appliances. And Jean Schweitzer and Henri Cuny will present work package 3, which was about testing for the hydrogen and natural gas blends and impact on different appliances. We'll have a coffee break around 11:20, 11:40. And then we'll have a presentation by Lisa Blanchard and Stéphane Carpentier on work package 5, which was the study of the appliances present on the field. And finally, a conclusion of the workshop and future perspectives and expected results for the deliverables that are to come for the end of the project. First of all, a short introduction to this event today. The workshop is being recorded and there is a streaming going on, and we will also use the video afterwards for dissemination purposes. If anyone is against being recorded, please let us know now. We can do just a close-up of the speaker. Otherwise, there might be some views of the room, probably from the back. So is that okay for everyone? Good, thank you. So on some slides, you will find the reference of the related THyGA deliverable document, like here, for example, THyGA deliverable 2.1. So this is useful if you want to take note of that, and then later the various deliverables are available on the THyGA website, so you can check out the information more fully. For the questions, so the streaming link that you received, especially for our audience online, there is a question box, so please put your question there. They might not appear immediately. We'll have just a filter of moderation, and the speakers will take what questions they can, depending on the time. However, we want to assure you that the project team will record all of the questions, and we will publish a written document afterwards, after this event, which will respond to all the questions. Please let us know your questions, and we will certainly come back to you. We're going to be using an online survey at a couple points during the presentation, so Slido. So you can use this code, please, for the people online. It's also integrated on the page. Normally, if you scroll down, you will be able to see it. And for the people in the room, so you know how it works, if you go to slido.com, also on the phone, and type in the numbers 2963366. And we're actually wanted to start with just a test of the Slido tool, and also to get to know better who is attending our workshop today. So we're going to go to the Slido page right now. And normally you should be able to see this poll. So if you could please connect to the Slido and let us know what type of organization are you representing. So, and apologies, the question is a bit truncated, but it says appliance manufacturers, gas industry, associations, academia, or other. I'll just leave it for a few seconds so that people have the time to respond to that. So this is for the speakers also interesting to know what the audience is composed of. And of course, we are we will record that as well for the final deliverables of the project, to see what type of audience the results are reaching. So that's interesting data from our side. I'll just leave it a few seconds. for coming in. I think we have quite a big audience online as well. So thank you everyone for joining. We're very happy to see the people in the room here in Brussels, but also everyone who managed to connect online. So quite a diverse group from what we can see here. So appliances, representatives of appliance manufacturers, gas industry, and as well other. Will be interesting. You can write us later to see what type of organization you are representing. Okay, thank you very much. I'm going to, though we don't have everyone, but I'm going to close the poll and ask a second question, which is going to be in which country are you based? So this is also just for interest for us to see the regional outreach of THyGA. Quite a lot already. So a lot of European audience, but also some across the board. That's very nice to see. Thank you for everyone who is joining us from a difficult time zone. We appreciate it. Still some people typing. Okay, thank you very much. All right, so a bit later in the presentation, I think we will have one or two other questions. So, you know, this is going to be the same code to respond to the Slido. Perfect, thank you very much. And so we're going to go back to the presentation now. And I can leave the floor to Patrick, our project coordinator.
Thank you, Alexandra. So good morning, everybody, and thank you very much for joining for that final event. I am Patrick Milin. I'm working at NG, and I am the coordinator of the THyGA project. I would say the lucky coordinator because it was really a good experience to manage that project and to go through all the steps, the complicated steps we had in the last 3 years to reach the results we are about to show you. I hope you're prepared because there are many slides, many information, but it's very well seen. A lot of very interesting information you will see today. I will spend a few minutes to come back on the context of THyGA, what we plan to do, where we are here, and what is the organization, of the project. So basically, we are here to talk about hydrogen. Hydrogen is one of the energy paths to decarbonization, as everybody is aware now. And today, specifically, we are talking about blending of hydrogen in natural gas. We are talking about injection in the gas grid, which is actually a challenge for end-use equipment and appliances. We are talking about new appliances, but also existing appliances in the field, as we will discuss a lot in the next presentations. Especially, we are expecting impact when the percentage of hydrogen is high, and that's what exactly we are looking at within THyGA. What are we talking about? We are talking about around 200 million residential and commercial appliances in Europe, and that's exactly what we target through our extensive test campaign. THyGA has been built as a consortium to answer a call from the FCHGU, the Fuel Cell and Hydrogen Joint Undertaking, now the Clean Hydrogen Partnership, subsidized with the European Commission also, to support the development of hydrogen and massification of hydrogen technologies in Europe. So we built this consortium in 2019. We are 9 partners here, so 5 labs doing the core of the project, the test. So we have D4GBE EBI and GBE in Germany. We have DGC in Denmark, GasBE in Belgium, and NG in France working really on the combustion aspects of the test. THyGA in France is also in charge of the non-combustion related aspects. We'll discuss that at the end of the project also. We're talking about leakages, for example. Then we have 2 manufacturers supporting the activity and making sure that the results we are providing, the direction we take is relevant for the stakeholders, meaning the industry. The results we have to provide are to be useful for manufacturers, for associations, for some technical committees. So it's important to have this discussion and this warranty from the manufacturers, which are BDR Thermea and Electrolux. And finally, Gurge is in charge of communication and dissemination of the information, and we have to thank them for organizing today's workshop. What are our expected results? 3 points. We have to close knowledge gaps. There are many information in the literature based on experimentation, on studies about impacts of blends on appliances. But there are gaps. There are things we don't know about, we are not so sure about. Generally, the test methodologies are not so clear. So it's very important to understand exactly what we are talking about when we speak about impacts. So that's really the priority of the project was to define what we were missing in order to prepare a test protocol to go further. Then we are a pre-normative research project, meaning that we have to support standardization activities. We are not there to make results for ourselves. We are there to make results that will be used by the industry, by the same technical committees, to support the development of standards and certification. So that's really the need we have to fill through the tests we are making. And finally, as a conclusion, we have to clarify what is acceptable as a percentage of hydrogen for the industry from our point of view, which is only the end use for residential and commercial. We will not speak for all of the other sectors, but still that's quite a huge gas consumers in Europe. Our organization, it's quite a linear organization. Work Package 2, led by GVI, is in charge of setting the basis of the project. So the segmentation of the types of appliances we want to test, the elaboration of the test protocol, and literature review about all existing knowledge regarding blends and the impacts of blends on appliances. And I take this opportunity to thank them because they couldn't join today. So we think about them, and they would have been a great asset for today's presentation, so we try to do. Work Package 3 is about experimental work. So it's led by DGC. This is the core of the project. We want to understand exactly what would happen on the field when we inject hydrogen in natural gas. So we are not talking about test gases or limit gases. It is really what would happen on the field. Work Package 4 about standardization. So now we are talking about test gases. How can we certify an appliance according to the percentage of H2 we imagine would be injected on the field? This is led by the GasBA. NG is in charge of coordination, Work Package 1, and also mitigation measures. So how can we increase the acceptable rate of H2 in the grid from the end user point of view? Are there some technologies, some methodologies to implement to improve this acceptable rate? And finally, communication, dissemination, and exploitation are in Work Package 6, led by Gurge. The strength of our project is not only the partners, which are very good, but also the very extensive advisory panel group. And actually, they helped us a lot throughout the project because we saw a really strong interest for the project from the start, with many associations for manufacturers, research centers, but also national associations or even international actors coming from USA, Canada, Japan, wanted to understand what we were doing and how we were doing that, and to take into account the knowledge we were providing to improve their own knowledge and then strategies. We also have many contacts with same standardization committees related to end use. So we have a list here, for example, and some liaisons within them. And that's quite important because it shows that the results we are providing are really used by the industry, not in a report in a closet. It has to be useful for everybody. And finally, we would like to thank a lot the manufacturers because actually they helped us a lot by providing many appliances that we had expected to buy, but actually we saw a lot of motivation from manufacturers to understand how their appliances would fare with blends. So that's actually 1/10 of the budget that has not to be implemented for purchasing appliances, but can be used for more tests. So it's very useful for us also to improve the knowledge sharing and gathering for the project. So many of these manufacturers provided appliances. We tested them, and it was also very interesting because we could have feedback on their appliances, on the test results we had. So in a word, it's a win-win combination because we learn more and they learn also. So it's very important for us and that collaboration. And we also have strong links with some European projects. Sorry. HIGS and Super P2G are two other subsidized projects by the CHP. They are addressing the same topic, blends in grids or injection of hydrogen in grids. So we have frequent exchanges with them. We also have some strong links with HyDeploy and HyDelta, which are two UK and Dutch projects, which we are working on the same topics with different approach, different methodologies, but very interesting topics, documents that could be shared with us and that improved also the way we were doing things or improving the work. And finally, we were lucky also to be exactly in the same timing that GERG sent a PNR project, so pre-normalization research project, which was deemed to understand the knowledge gaps for certification. So actually it was also a very good win-win for us because we could provide them inputs about what we knew, and then we took away the expectations they had for PNR activities in order to improve our reports. History of the project. So that's not my best slide, it's very simple. The project started early 2020. It was due for 3 years. As you all know, we had some pandemic issue in between and right at the beginning of the project. I mentioned that because it was actually quite complicated for us to start testing, for example, and it created some delays that are quite habitual in these kinds of projects, but it had quite some impact for us. We had we had to make a lot of meetings, especially with stakeholders on advisory panel, to make sure that everybody understood what we are doing. And that's actually today the second physical meeting for the project members. So it had also an impact on us, but I think the team spirit was still very good. But it means that it led to a 3-month extension demand to the European Commission to finish properly the reports, to make sure that we were not in a hurry and had time to analyze properly every test results. So that's why we are here in March now this year, and you can expect a lot of reports being published in the next weeks, by the mid-April or a maximum. Okay, now just a small comeback on the targets of the project. When we built the consortium, the target set by the European Commission was to assess operation, behavior, and safety aspects of appliances up to 60% in volume in natural gas. That's quite high. When we started in 2020, actually we had some discussion and thinking maybe it's better to focus below 40%, because yeah, it's more what we had expected at the time. During the first public workshop with the stakeholders, so all of you here, we had an online survey, and actually it led in May 2020, so 5 months later, and it led to almost everybody predicted blends lower or equal to 30% H2. And then in terms of perspective to 2050, more dedicated hydrogen grids. So that was the tendency 3 years ago. And so today we would like to have another slide survey to understand exactly how your perspectives evolved. So we have the same questions exactly, and we will try to check what do you think we should go through in terms of blends. So I think you can connect on the Slido. It will come soon. Maybe it's online already. Okay, here it is. So, which level of hydrogen admixture do you consider realistic for 2030 in the distribution grids? It's a bit stressful because the conclusions of our projects are in line with that, so it's better if you answer as we like. we are quite good, I think. Okay, so it looks like below 20% reaches around 80% of the answers, which is actually what we were planning to focus on. So, of course, in the reports, you will have results up to 60. It was the contract, so we made it. But today, we deemed it more relevant to focus on below 20 because it was our feeling that it was the tendency for the stakeholders. So, thanks for answering as we wished for. Thank you very much. We have a second question on the survey about the perspectives for 2050 to see also if your opinion evolved. So if we can come back to the Slido. Thank you. So perspectives to 2050. It's slower. People have to think about that. Okay, so it's more or less the same trend as we saw 3 years ago. We're seeing that people think that dedicated pure H2 networks would be the realistic situation in 2050, even if I think we also have some percentage at 50%, which was not in the last survey. So it's also something to look into. But it's good, we have the results for that. Okay, thank you for voting. So of course we will include these results in the presentation we will publish online, and it will be in the reports also to have some perspectives. Today's workshop, what will we discuss about? First, a few slides just to remind you a little bit about the segmentation and the state-of-the-art we made in the work package 2. Then we will discuss about the new appliances and certification, the work done by the work package 4. Before going to the core of the project, the extensive testing results we have from the 100 appliances we tested in the project, in work package 3. We have this rec, and then we will discuss about these existing appliances on the field. They are installed, but how about their environment? How about gas lines, about fumes? Will everything work correctly with blends? And finally, we will have some conclusions to share with you also. First, about segmentation. THyGA's purpose really is to be a very extensive project in terms of number of appliances to test, around 100, as we said, but also the type and the variety of systems we want to test. As you know, we have 200 million appliances installed in Europe, but there are not only boilers or cookers. There are many kinds of appliances for catering equipment, for example, but also air heaters, radiant heaters, fires, cogeneration, gas heat pumps, and all of these have their own specificities in terms of combustion, of design, of controls. And of course, to understand clearly what would be the impact on the field, we have to dive into that and look into everything. We cannot focus only on one type of appliances or another. So the first part of the project was to build this segmentation, which was based on a Gasqual work done a few years ago. We added some segments, and we reached around 60 appliances type, based on the typology and use they provide. For example, boilers for heating, space heating, for hydronic space heating, or fires for heating air in a room. And then within these big segments, we have different typologies based on the combustion. For example, fully premix boilers or partially premix boilers, open flue or not. So it makes a lot of segments, around 60, and our goal was to test all of them. It was not always possible because some were not available anymore, for example, or we didn't find the appliance, but we are close to filling all the gaps we have related to these appliances. As you will see in the work package 3 results, we will show you a very fast synthesis of the results for each of the segments. That's really the strength of our project, to show that we can look into the behavior of each of these appliances. But it takes a lot of time and a lot of energy. What is important there is that using that segmentation, we can also provide each of the 10 technical committees with the information related to their own activities. And that's what we will do in the next months to go on disseminating the information. So what you will not find today in the workshop will be in the reports, or the members of the project will participate to meetings, technical meetings, to provide you with more information to dive into what we did in the last 3 years. Second step of the project was to understand where were the gaps in the literature. So it was a very extensive literature study based on published documents, but also experimentations, discussions with manufacturers, associations, to understand what were the phenomena we could find relevant to study within the THyGA scope. And actually, we had different agreements and disagreements, as you can see here. I will not go into the details. There are some reports available on the SharePoint, on the website, sorry. But it really confirms the need for an extensive and documented test campaign where everybody can find the information. And that's also important to notice that most of our work is public. The test protocol, the test results, so it means that you can access to all of that, understand exactly what has been done and the conditions of the test. So really, this is one also of our strengths here. And with that, I'm closing the introduction, and I think we will, I'm sure, we will begin discussing about new appliances and certification with Chris DeWitt, who is joining us.
Okay, so good morning. My name is Chris DeWitt. I'm working for the Belgian Gas Association called gas.be. And indeed, so first we talk about new appliances. New appliances, as you know, have to be put on the market and taken into service certified. I think the new appliances are probably not the biggest challenge. I think the biggest challenge is on the big stock of installed appliances. But nevertheless, also certification and standardization for H2 natural gas admixtures is, of course, an important element. Yeah, one thing to start with is to say, well, okay, it's not. People tend to forget sometimes that hydrogen has been used before, also for residential end use. So there has been town gas, as it was often called. It was still in use, like for in Belgium also, it has been used before. Natural gas has been introduced in Belgium, so and there has been a conversion from town gas to natural gas in the 70s till the early 80s. But already at that time there was a conversion from about 1.5 million connections to the town gas, and then compared to the 3.6 million we have today for natural gas in Belgium. So, and there is even in a standard, the N437 standard, it's still existing also. It's called the first family of gases. And also that is important, so it already contained, or it contained 50%, around 50% of hydrogen, so more than what we saw here in the questions we have asked already this morning. So it's not longer in use, or at least not, I think, for any residential or domestic use in Europe today. It was also used at a lower pressure, but okay, it did work well. Okay, I know technologies have changed, and also requirements have, of course, are like environmental requirements, etc., are stricter than before, and technologies have, of course, also evolved, have also changed. If we look first to the certification framework, the current certification framework, gas appliances in Europe need to satisfy requirements of several directives and regulations that are enforced, depending also on the type of appliance. And some of them are impacted by hydrogen or hydrogen injection in natural gas. So, and I think, yeah, one of, or maybe the most important is the gas appliances regulation, often abbreviated as GAR, or referred to as GAR. So covering gas safety risks and also energy efficiency requirements, where for appliances where its energy efficiency is not covered yet, and that's already the case today for a lot of products in the Eco Design Directive and energy labeling regulation. So, but another thing not to forget, it's not, I think, the current certification framework, or certainly not for products, but also to keep in mind, because that will also come back, is that you also have sometimes national or regional regulation that is in force, and that also imposes efficiency and emission limits to be measured on site, so with conditions of the day, if you want, so conditions of gas quality, conditions, the other ambient conditions, and also those have an impact. Due to that, you see sometimes, so I also think then of a situation we have in Belgium, also there, yeah, then people, our technicians, installers tend to adjust appliances, the combustion settings on site, to satisfy those requirements. Okay, here there is a lot of text, but I think it's also important. If you look to the gas appliances regulation, well, first of all, and that's of course good to know, that is that okay, the mixtures are within the scope, and also hydrogen, 100% hydrogen would also be in the scope of the current gas appliances regulation. And then something that is considered in the considerations in the beginning of the text, and I think it's very relevant also for the further presentations today, is that the composition and specifications of the types of gas at the place where an appliance is put into service is very important for its safe and correct functioning. And therefore, it should be taken into consideration at the design phase. So the manufacturer needs to take that into account at the design phase. So the manufacturer also needs the information of relevant gas quality parameters to be able to design appliances that do satisfy the essential requirements of the gas appliances regulation. So then they also, okay, then translate that in saying that appliances made available on the market and put into service when normally used, so when normally used is defined, and one of the things it says is that it means used with a normal variation in the gas quality. And what is then normal variation of the gas quality? That is set out by member states in their communication, so it's published in the official journal of the European Union. So, but I think that's a very important element. And then, of course, yeah, we all know that's why we are here today. If not, there wouldn't be this project. So mixtures of hydrogen and natural gas, they may compromise existing appliances' conformity to one or more of the essential requirements. Yeah, and then I think also a very relevant aspect to keep in mind is that manufacturers in a way cannot be held liable. I'm not a manufacturer, so I'm not biased when saying that, but so it's cannot be held, and I'm not a lawyer neither, but cannot be held liable for appliances that are on the market and that eventually would not satisfy all essential requirements when supplied with hydrogen natural gas mixtures, because it's not considered as normal use. It was not communicated before. No specifications were given of any relevant hydrogen concentration in the natural gas. And then, okay, if we want to go to a market where hydrogen is injected in relevant quantities in natural gas, then there is an interest of publishing that in the specifications so that manufacturers can take it into account. On the right you see a table where it indicates already what some countries that indicate today already a hydrogen concentration in what is published in the official journal of the European Union. Yeah. And then finally, yeah, I think that's also important. You often hear, or authorities also, or other people ask, yeah, but okay, are appliances not already fit for the use of hydrogen injection in natural gas? Because they know that, and it is true, since decades now, we have already a test gas that is used, a limit gas that is used for testing one specific risk on appliances. So it's certainly not a guarantee that with the 23% hydrogen it contains the test gas, that all appliances do satisfy all essential requirements when using that gas. So it's only used for one specific testing, assessing one specific risk. Okay, that's the certification framework. There is more to say, but we don't have time to go deeper into that. As far as standardization is concerned, but because then, okay, essential requirements are formulated in a very general way, but then you have standards translating that in concrete figures and requirements. So, and there are, I would say there's one kind of, I'd say a horizontal standard, if you want, which is used then for the different products, and that's one, the EN 437 standard, which is defining test gases, test pressures, less relevant for today, what the topic of today, and appliance categories. And that's TC 238. Okay, they started also working on revising the N437 for this. And then you have the gas appliance standards. You have a lot of technical committees in CEN that are working on different kinds of products, gas appliances. And they are, some of them, like TC 109 on the boilers, is already well advanced on integrating mixtures of hydrogen and natural gas. Others are also starting or are also or still need to start. And finally, also, and that's of course relevant for the different products. Also, there is also what is called in the gas appliances regulation a fitting, but it's components that are used in gas appliances. So you have TC 58 on very important, obviously, safety and control devices. And then on the left, you see a map. I think you can't read it, but it's just to indicate there are a lot of committees working as well on European level as ISO level, working on hydrogen, and not only on end use, of course, also upstream. A lot of upstream matters, and it's not about it's not a competition of being first, but many things are going on, and that was also one of the challenges in the project, where we saw that we are in parallel working with the work that was going on, like for instance in TC 109. If you look to the N437, I think that's very relevant in the certification framework, assessing appliances for the use of H2 natural gas. So first of all, they define a gas family. So and a gas family, say that's a group of gaseous fuels with a similar burning behavior, linked together by a range of Wobbe indices. So a Wobbe index is an important, the most important, or at least one of the most important combustion parameters that is used, and is kind of interchangeability criterion. But okay, what is considered similar burning behavior, if you know that compared to, because natural gas is the second family, if you inject hydrogen, then up to what concentration, hydrogen having very different properties, up till what concentration can you consider that being similar burning behavior? Can also change the definition, of course, but those kind of things are to be discussed in TC 238. If we look to a gas group, we have a gas group is a specified range of Wobbe index within that of a family. So within the natural gases, you have like H gas, L gas. You have the E group. So I should talk about groups. So H group, L group, E group. So different groups, and they are determined on the general principle of that appliances using the gas group. This gas group operates safely when burning all gases within this range without adjustment. That without adjustment is important to say that in current practice is that there is a lot of adjustment, and it's also allowed specifically in some countries. And there it is important. So on the left, what you see, I don't know, does this work? Yes. So what you see here, so on the left you see a Wobbe index. On the x-axis, the horizontal axis, you see hydrogen concentrations injected. And what you see, and that is very important, is to know that, as soon as you inject hydrogen, the Wobbe index of the natural gas, this is methane. Not methane, so the different points, this is methane, the orange starting point here. But the others are the different test gases used today in EN47. But okay, you see that for each gas, you are lowering the Wobbe index. And then you come into discussions like this are the limits of the H group. And that means that if your natural gas can can have a Wobbe index over the whole range. As soon as you start injecting and you have a natural gas located here, then you are getting out of the limits of the group. So and then, okay, you have a choice of, okay, extending the group to cover all possible Wobbe indices, or you have to limit the natural gas Wobbe range. So for instance, if you look to the 46.44, which is the lower limit indicated in the, yeah, it's not very important, but because everybody, I don't think everybody knows, but okay, there is an easy gas, a common business practice defining also H gas, and which defines the lower limit on 46.44. But then you could only inject 7% of hydrogen to respect the limits here. Then finally, yeah, also appliance categories are important because they are identifying the gas families and gas groups appliances are designed for to operate safely. And also, I think as important as operate safely is also to the desired performance level. And that is also one of the reasons why, if that is not the case, that appliances eventually are adjusted on site. Because we know that fluctuating H2 concentration between, for instance, 0 and 20%, so then it will be, if the local range would cover all of this, by adding 20% in whatever case, yeah, then you would have to extend to this point. So that the local variation may be wider, and that also has challenges. If you look to the different gases, so this is, I will pass over this quite quickly. But there is we look, so on the left, the limit gases as defined in EN 437. So we use limit gases to test specific points. So you have incomplete combustion and sooting. You have flame lift. So incomplete combustion happens with the high Wobbe index gases. Flame lift or flame instability happens on the other side with low Wobbe index gases. And then a specific phenomenon is light back, so when a flame front is going closer to the burner or eventually even back into the burner. And finally, also there is an overheating gas. If you have to consider H2 natural gas use, so a mixture of H2 natural gas, then okay, there are a number of things to be considered. So yeah, the upper one can stay because it can also be 0% hydrogen, so it has to be kept. On the lower end, it has to be, or we keep the current limit, or we also have to go to a lower limit. And then you have you have the, yeah, what is the G22, on G222. Here we have, and I don't think we have the time to go into detail, but there is to be considered also because it's mainly due to flame speed that is increased due to the hydrogen injection and it's technology specific, so depending on the appliance, and that is what we also see on the right. So all what you will see as graphs here on the slides, they can also be found in an existing published deliverable, 2.3 or 2.2, I do not know about 2.3, I think. Yeah. So and then, but depending on the technology, whether so what you see here is on the x-axis the equivalence ratio, which is 1 over lambda, if you want. And on the y-axis, the laminar flame speed. So, and then depending on the technology, whether it's a technology where the lambda or the equivalence ratio stays constant, then it's, because the yellow line here is the flame speed depending on lambda, or in this case, the equivalence ratio of methane, then of methane with 30% hydrogen, and then finally with 50% hydrogen. But okay, what you also see is a shift in lambda when you use it in an appliance without adjusting settings, and then you get a kind of phenomenon like this, where you see that the flame speed hardly increases. So and then you have to consider whether it is the appropriate gas that is used. But I think okay, I'll have to stop there also for this point to make sure that we keep up the pace. So there is also a reference gas that is used. I've mentioned the limit gases. There's also a reference gas, which is a gas with which appliances operate under nominal conditions. when they are supplied at corresponding normal pressure. And the reference gas is used for testing a lot of different risks, or assessing a lot of different risks. And there also it's considered to, besides the current reference gas, to use or to create a second reference gas that is used for all or for part of the tests that are done with reference gas, so reference gas with the maximum hydrogen concentration. So if you consider 20% injection, well then methane with 20% hydrogen would be a second reference gas that would be relevant. And then, okay, there are also discussions on whether, okay, do you need then to consider that you do testing where appliances are specifically set for the reference gas, or one setting for both, or whatever. Then finally, if you look to risks, and because it's all about risks, if you have to review existing standards, then it's about, okay, what are the risks introduced by injecting hydrogen in natural gas? And there it starts, we think, with the properties of hydrogen, and they are very different from methane. And so they do increase eventually certain risks, or some new risks. And so that needs to be tackled also in the work done by the technical committees when reviewing the standards for H2 natural gas mixtures. So, and those risks are related to safety, but also to performance, like emissions, efficiency, and also fitness for purpose, because of course it's also important that the appliance still does what it has been designed for. Yeah, okay, in the work, not in what to show on the next slides, but yeah, it's also in the deliverable that will be published soon. There's also a link to the corresponding gas appliances regulation essential requirements, and also in a more extensive way, the findings of work package 3, which will be presented by Jean soon now. Where to make the link between both, and specifically for 20% hydrogen, which is I think the case which is most looked at. Very important to consider is because what I show on, or what is presented on the next slides are a few examples, because there are many more. But it's important also to consider it's not because there is, due to that property, a new or a risk that is increased. It does not mean that in reality it will be, the risk will be higher, because it's possible that it's compensated by another phenomenon, like for instance the lambda increase, so the air excess increase, let's say. Yeah, we are not going to go through the table, but there are a number of properties listed of hydrogen compared to methane. Methane being the main component of natural gas, and then you see, okay, there is like the gross calorific value, or the calorific value in general, which is very different, which is only about 1/3 of the one of methane. The relative density, there is also a very important difference, which is also very relevant. As far as Wobbe index is concerned, it is a little bit, the difference is not that big, but it is also very relevant, and we've seen on an earlier graph that it always lowers and also widens eventual local Wobbe index ranges. And so you have other relevant things, of course, also the methane number, for instance, which is 100 for methane, and which is 0 for the other, for hydrogen. So, okay, we'll now just show a few of those. I think in the deliverable there will be a lot more and more developed, but there is no time to look at that. And I think the main challenge, as I said in the beginning, are the existing appliances and not that much certification, without saying that the certification and standardization is not very important. So what we see here is, for instance, the fact that there is a lower minimum air requirement, very significant difference between methane and hydrogen. So you need less air for a complete combustion of 1 cubic meter hydrogen compared to 1 cubic meter of methane. And that is very relevant, and that also leads to an increase of the air excess. If you do not change the air flow, volume flow, then when injecting hydrogen, then the lambda will be, or the air excess will increase, depending also, of course, of whether an appliance is equipped with auto-adaptive controls or not. But it goes, it increases like this. So for most appliances, it's this case with constant pressure and constant volume flow. So which leads to a relative increase of lambda of what you see here. But that has certain consequences. So the fact of having more air also can lead to people tend to think that, or people in the business, of course not, they know very well, but that it's only when you put in a very rich gas, a very high Wobbe index gas, that you come to that you have lack of oxygen to burn all the methane, for instance, and that then you start creating CO or concentrations that are way too high. But it also happens on the other, and I think Jean will also show some graphs that give a better view on that. But okay, what happens then is that if there is too much air, then you get unstable combustion or eventually flame lift, which also gives rise to incomplete combustion in a way. And also, of course, all I say here is also depending on the concentration you are looking at. I think for most of the 20%, for instance, if we look to the specific 20% case, it's not really a issue for most of the appliances if they are on the factory settings, if they are not adjusted on site, but more on that also later on. And then, okay, if in extreme cases it can also lead, the flame supervision device will also shut off the gas supply eventually if it's too strong, the phenomenon, and before reaching a certain CO limit. And eventually also, it also leads to a lower efficiency. Other things like, okay, the lower Wobbe index, we have already said that. So as far as Wobbe index is, for those who would not know, so it's calculated by the calorific value divided by the square root of the relative density. So what you see here is Wobbe index and calorific value, gross calorific value. The gray line is the gross calorific value. The yellow one is the relative density of methane in this case, and then up to 100% hydrogen. And then, okay, that results also in a Wobbe index that evolves like this. So, but that is important. And if you look to appliances without making too much, because there is lack of time to go into the different technologies. But what happens with air excess, what you see on the right here, is also again on the x-axis the hydrogen injection, and there the air excess ratio and the firing rate, or the heat output. So what you see, the heat output is the yellow line, the lambda is the gray line, and then the gas volume is indicated here as the, what is that, red-brown line. So, and there, what you see is that it increases, so the gas volume increases. So that is also an important aspect. But the lower Wobbe index, that can give rise to like insufficient heat input, heat output also by consequence if the efficiency stays the same or lowers. So, and lower heat input is not necessarily a safety issue, but can be an issue of, for instance, instantaneous water heaters or of fitness for a purpose, so that people would complain about not having sufficient output. So, okay, it's not for 20%, it's not that important in a way, or you could think that it's not that important, because it has a 40% lower energy content, so calorific value, the mixture with 20% hydrogen, but it's increased by an increased gas flow in the appliance, so which brings it to a difference of about 5%. But 5%, it also depends, of course, because an appliance is set for G20, but if the natural gas supplied has a much lower Wobbe index, then you also have the natural gas difference, and then it increases the fact that hydrogen is added, still increases this fact. And then you have other points also related to that, but I mentioned them already. But you can also have CO concentration being too high due to that, again to the increase in air excess. You can have overheating of burner surfaces, not resisting a long time to those higher temperatures, for instance. So material damage, deterioration. And eventually also practical problems, operational problems like no ignition and extinction. And that, all of that you have, also adjustment on site is a very important aspect, as it is widespread practice. It also needs to be looked at closely to reconsider some of the current practices to do this adjustment. In a way, today it is done in a, I would say, kind of blind way, or only based on readjusting to a CO2 or O2 level, which is indicated by the manufacturer, but without taking into account, in many cases, the current or the actual gas quality at the moment of making the adjustment, and also the ambient temperature, if, for instance, the air is taken from outside. Yeah, there are other things. This is partly because, I said, sometimes it can be compensated or even compensated widely, so that in fact there is a reduction. Like for instance, of the phenomenon. No, it's here. Sorry, it's here. It's the flame speed. So what we are showing here. So it's a graph that exists already since a long time. I think from the University of Groningen already in the early 2000s that it has been presented by Howard Levinsky. So what was said there is that there is a difference between what are called the full premix appliances and the partially premixed appliances. But I think regarding the timing that we'll not go into that right now. So, but that is a very specific and important thing to consider. The light back. There's often the term used is because you will hear flashback, light back. It's referring to the same thing generally, but in the standards normally it's light back is used, but it's talking about the same thing. So flames entering into the burner eventually due to a faster propagation of the flame front. So where the equilibrium between the gas flow out of the burner and the flame front moving to the burner, where the equilibrium there is disturbed. And I said, there again, if the burner front comes closer to the burner, then of course you have also this temperature rise of the surface, the burner surface, which is also eventually a problem if the material does not resist or does not resist over a longer time. There are higher flame temperatures, but I think it also comes back later on. So I will not go too deep into that neither, because this is typically something that is easily or is compensated, because the higher flame temperature, you have NOx, nitrogen oxide formation, which is mainly the main source is heat temperature, thermal NOx formation. And there, so then due to the higher flame temperature of hydrogen compared to methane, it gives rise to more NOx formation. But there typically that is something that, so here you see NOx formation also in function of air excess. But as said, in many cases of the appliances you will see a shift in air excess, so more air that is applied to the mixture, to the fuel, so which makes that it is compensated and even reduces sometimes, or in many cases, the NOx formation. That can eventually be different if there is a combustion control, but not necessarily. And I think the results will also be shown of what has been done there. And in the end I also mentioned, but there are many things, I think we cannot go through everything, but as said, the gas flow increases, the air volume flow stays the same, so then in the end it results in more combustion products volume, and that also has eventually an impact. If you have to evacuate bigger volume there, then eventually appliances equipped with like those like B11 appliances. So they, with a draft diverter, they will, the thermal safety device eventually is not maybe at the right place anymore, could be needed. But for 20%, generally we do not see a lot of issues, but I heard also from manufacturers that it can be a limit, and that it's certainly something to be looked at also on a case-by-case business. And then as said, there are many things. This is the last slide I'll show. There are many more even than this, but there are other things to be considered. So we don't have the time today. We put the accent on the existing appliances and the tests that have been done. So, but another aspect to consider is also delayed ignition. Normally an appliance ignites, or the idea is to ignite as soon as possible to get stable ignition of the burner. And there is a certain safety time that is used. If after a certain time, when it reaches the safety time, it is not ignited, then the gas supply is shut down. But if it's also here, what you just can see is that, so here it is used, this is a test on a boiler where you have so the test with the reference gas we use, methane, so nothing with hydrogen. If you replace it with a setting for G20 or for methane, and you replace it with a mixture with 30% hydrogen, it becomes more violent in a way without any deterioration, a difficult word to pronounce. To the appliance, so no product damage, but okay, you can hear that there is a difference, that it's more violent. And then okay, if you do that with the same setting, if it's adjusted on site, for instance, or in the factory, whatever, but okay, if it's adjusted specifically for the mixture with 30% hydrogen, then of course, yeah, you also increase again the energy content. And then you get to, if you, because here it's 1 second, 2 seconds, 3 seconds, 4 seconds, etc. Just to before, just up to the safety time. But then you see that already it comes to a point where also there, here in this specific case, it was not a problem, not an issue as far as the appliance itself was concerned. But okay, you see that it's more violent, and depending, you also have appliances with glass-fronted appliances, so with big combustion chambers, etc. It is too specifically to be looked at, I think, also on a case-by-case business case. So, and also their tests have been done also on this kind of appliances for delayed ignition. But as said, there are many more. You see here the knocking, and specifically for engines, for instance, like based on methane number, that changes a lot by adding hydrogen. But I think that's what I wanted to tell today. I think important there is maybe just to say that, okay, in the deliverables there will be more. I think in the different TCs, and especially TCs that are maybe less advanced than others, it could be interesting, and we are open to come to explain more in detail what our thoughts are on all of these matters. So thank you very much. And the next one is Jean, I think, or who is next? What's? Ah, okay. Yeah, and is there a password, or because it's? Couldn't recognize you. It says.
Few questions. I will refresh the page. Maybe you can show them, Alexandra, with your computer in the meantime, because I need to log in again.
Anyway, there you go.
Yeah, okay, somebody asks what type of control devices are considered in the fitting standards. Well, there are a lot of different standards. I think some people know better than I all the different control devices that are considered, but of course there are the gas valve, there are the controls, the air-gas ratio controls. But I think it's also on other things like, but that are maybe not always relevant. Although, there was also pressure regulators that are eventually incorporated, etc. So many different control and safety devices that are used in the different appliances. Should the amount of hydrogen blended be limited to the incoming gas quality? Yeah, I think it's a justified question. It's also something maybe hard to manage. That's something else because it can quickly change, of course. So depending on the gas quality of the base gas where you intend to inject hydrogen or where you are injecting hydrogen in, you could also imagine indeed in function of how it changes to adapt the hydrogen concentration you inject in. But that requires, of course, also a system that allows to check the actual value of the gas quality. So, but I think it is relevant. Yeah. Yeah. Okay. So there are more questions, but to respect, because I think we are now a little bit behind, a few minutes already behind schedule. So there are some more questions, and they will be also, as said before, they will be answered in a written form and will also be published. So thank you very much again.
Good morning, everyone. So I'm Jean Schweitzer from the Danish Gas Center, DGC, and I will present you the VP3, so the experimental part of the project THyGA. So I will come back on the objective first and tell you a bit about the test protocol and the parameters that we have been studying. We will talk about the working methods. And after that, we will come into the results that you are waiting, both on the short-term tests that are tests in laboratory that are performed in 1, 2, 3 weeks, and also some of the tests we have done over a longer period of time. And after that, we will bring the conclusion about the percentage of hydrogen that we believe could be tolerated by the appliances that are installed. So just coming back to the contractual part, our work was consisting in 3 parts here. First, to elaborate on a test protocol with the detail of the testing, what parameter to test, how to test them. And this was also kind of a very tough job because in a way we had to build up a kind of standard for testing appliances with hydrogen. And normally when you make a standard, it takes about 10 years, and we have to do that in a few months. So of course the standard we have done is not a perfect one, but it suits the purpose of the project. We had to test 200 appliances or so for the sake of the project. Then the second was to execute the test. So as I said, we were having a short-term test and long-term test. And then there is a third part, which is looking at the tightness of the indoor installation, which will be part of the next presentation. So not after me. So starting with the test protocol. The test protocol is, in fact, as you can understand, giving the detail of how to test to the laboratory, so to guarantee the best possible, or as far as possible, that we are testing in the same way so that the results that are obtained by the testing are comparable. It also includes all the, let's say, logistic part of the testing, which is getting the appliance, how to make the reports, and how to express the results, and so on. So this was a very big job, and we have also, just important to be said, is that the testing program has been discussed during the project with the stakeholders, with the CNTC especially, and this was, yes, there is a graph, I don't know if you can see that, but it's basically say that the stakeholders were happy with what we have, how we have designed the test protocol, and of course also I have to say that the test protocol was also taking into account all the comments we have got from the TCs. As mentioned by Patrick, there has been a number of things on the hydrogen front since we started the project, or since we made the project proposal. Some of the points are mentioned on this slide without going into the detail. I just want to insist again on what Patrick has said, is that basically when we started, we were seeking about 50-60%, and when we look at the real world, we can see that the target, a realistic target, would be more going to 20-30%. So about the gas we have used, of course, hydrogen, but we have also to discuss about what kind of natural gas should be used for the blends. And for that, we have used statistics from the Commission about the gas distributed in Europe. And we had defined then, we have to look at to the limits of gas, which are 47.63 as the lowest value of VOB distributed in Europe, and an upper limit as well. And we have called those two gases EU low and EU high. And then we have mixed two gases with hydrogen to create our test gases. And that you can see on the right side of the screen. You can see the VOB index and the density, and you can see how the two parameters are involving when you inject hydrogen in it. I think I cannot use, okay, well, I think it doesn't matter if I use the pointer, because all the people that are online will not see that. But if you look at the two lines, if you look at the right part of the line, this is a gas characteristic without hydrogen. And when we go down to the line, you can see the evolution of density and VOB index when you inject hydrogen up to 60%. So what we have tested, we wanted to test different things. We want to test the safety, energy efficiency, emission, and operation. We want to be sure that even though an appliance is safe, if it doesn't work as it should, so it's not really interesting for the end user. So therefore, we have measured a number of parameters that are related to the four aspects we want to test. And also, we have varied a number of parameters so to check how the appliance will react under different operating conditions, which are, for example, hydrogen content, but also the gas composition or variation in the pressure or things like that. And of course, adjustment, as we will come back to. And also maybe very important to say is that the philosophy of the testing we have done was to simulate, or try to simulate as much as possible, what is happening in a real situation. That means in a real situation, you have an appliance in a house, and the gas can change from day to day without the end user can really make anything on the appliance to possibly compensate or adjust for the gas that is coming to his house. So it's kind of things happening without we change anything on the appliance itself. A part of course, the adjustment, which is something specific, of course, in this case, and I will come back to that. So from that, we have built up a program that is covering the different aspects, so performance, safety, and operation aspect. And we had a list of tests you can see here. Will not, you can read them yourself, but I will come back, maybe define a bit more in detail what we mean by plug flow, flashback, adjustment, and delayed ignition. Delayed ignition, as it was covered by Chris, so I think we will make it very short there. Also, all the things that Chris has shown about how flame speed is impacted by hydrogen, according to the air excess ratio, all those things have been taken into account to design the testing program. So we wanted to test especially the test situation where there was a higher risk of having hydrogen for the appliance. So we had, in a way, as usual, when you do tests, you try to test the most interesting point. There is a limited budget for doing the test, so we have to concentrate on the aspect that would bring the highest added value for the understanding of hydrogen impact on appliances. Okay, this is very important to understand that, and that's also the reason why we will repeat that several times for this workshop, because this is one of the main outcome of the whole project. The adjustment. So what do we mean by adjustment? As in practice, when an appliance of a category H, so the gas that is most distributed in Europe, are coming out of a factory, they are adjusted for having the best performance with pure methane. When we say adjusted for having the best performance, it's a kind of compromise between low emission, low CO emission, low NOx emission, and the best efficiency. When the appliance is leaving the factory, is installed in a place, in some places, like Denmark, for example, there is a systematic readjustment based on the gas that is in the net. This is very important to remember, because this will be the source of issue we have with hydrogen. So when people are readjusting, so the installer, they are using technical documentation from the manufacturer, which is stating what kind of air excess the appliance should be installed with. So the air excess is typically measured with CO2 value in the flue gas or O2 value in the flue gas. So in the technical instruction of the manufacturer, it states this appliance should be installed with 9% CO2 or whatever, with a tolerance of plus minus, for example, 0.2%. So installer is putting his appliance on a house, and then he he measures the combustion and say, okay, I have missed a bit air, so I will increase a bit the volume of air that is mixed with gas, and to reach the value that is fixed by the manufacturer. What is happening is if you have a very poor gas in an installation, like for example, if you are in a country like, for example, in Denmark, where you have a lot of biomethane, so biomethane is at the lowest range of the Vohm index. So if you, one day there is a lot of biomethane in the grid, and also you have hydrogen, then you adjust the appliance, and then the volume of air needed for a proper combustion is for example, V1. And then if the day after you make the adjustment, there is a rich gas coming into the net, so for example, you remove the hydrogen or you have a heavy LNG, then suddenly you don't have enough air for a proper combustion. And what is happening there, so the O2 is going to move on this line here, and this is a typical pattern for oxygen, for CO formation as a function of the air excess or oxygen. And you can see that if you're going to miss air for the combustion, you're coming close to stoichiometry here on the left side of the curve, and then you will have high CO. And this is a dangerous situation. Okay, I will come back on that again, but I think it was important to understand that. Sorry? Oh, sorry. Okay, what about the scenario we are going to simulate for the project? So, as you know, we are in a period where we are trying to decarbonize the gas grid. So, and also we have a period where there is a security of supply for the gas. So there is a lot of new gases coming on the European market. There are, besides the pipe gas that is already there is more and more LNG gas that have higher Vogel index compared to pipe gas. And besides that, as you know, also biomethane is going strong in many countries and is blended with natural gas. And in general, biomethane has a lower Vogel index, slightly lower, but still in the range that has been mentioned by Chris. And on top of that, now we are going to also to inject hydrogen. And the injection of hydrogen also up to a certain value. But also very important to be mentioned is that this value of injection will probably not be constant. That means it could be 0 one day, it could be 20% or X% the other day. So this is very important. And this is the situation we are trying to simulate during our tests. So that means that we are trying to take into account the existing gas quality that is in the grid already, so EU low, EU high, and also the fact that now we will also inject some hydrogen without changing anything on the appliance, once again. Okay, so the testing protocol, for the testing protocol, we have imagined different scenario for adjustment. You can imagine that with all what I've said, you can really make a lot of scenarios. You can make EU high, EU low, with hydrogen, without hydrogen. You can adjust, not adjust. So if you combine all two things, you have really a multiplicity of scenario. So we have at the beginning work on a number of scenarios. After a certain time, we ended to 4 scenarios that are important, which are on these slides. Without going into the detail, I will just focus on the most important scenario, which is scenario G, which has appeared to be the one with really where we might have problem, or we think we will have problems if we don't make some action. This scenario consists in having a gas with a low Vogel index. Again, it is a situation I have illustrated with the U-curve a few seconds ago. So you have a low calorific gas in the grid, for example, a lot of biogas or biomethane, and then you put some hydrogen in it, and then you make the adjustment because the installer coming in a house don't know the gas which is in the grid, so he just do the adjustment or the operation on the boiler without having any information in general about what kind of gas is within the grid. So he makes his adjustment with this poor gas in the grid, and then after that there is a change, and we are going to a LNG gas type or a North Sea gas. This could be a scenario for Denmark, for example. And then with this high calorific gas value, you can also have possibly hydrogen. So this is adjustment. I will come on the results in a few seconds. The second thing that I like to define is the rate of change. So the rate of change is defined as a very quick and fast change of the gas quality in the grid. So, for example, you can imagine that when there is no hydrogen, then you would start to inject that. You have a front of gas, of natural gas, and just below that a mix of natural gas with hydrogen. And what is going to happen if this this situation is happening to a gas appliance, what will happen in the few seconds where the gas is changed. So this is something we have changed there. We have tested here. Flashback, probably you know, but maybe you can just illustrate with a picture here, showing that the flashback is a situation where the flame is coming completely or partially below the surface of the burner. And this is something, as Chris explained, because of hydrogen, you modify the flame speed, and this modification of the flame speed can bring some flashback on some type of appliance, especially the one that are having a lambda or air excess below 1 in the front flame. So you can see on this example here partial flashback as well on a Bunsen type burner, which is not a realistic situation, but you can see that on a cooker burner on the photo on the left. And you see the evolution. It's not something that is happening like chalk. That's certainly we have flybacks. It could be quite of progressive phenomena, and after a few minutes, you can see the flame appearance between 15 seconds and 8 minutes is quite different. But if you just stay in front of the burner, you probably might not see it as clearly, and when you see it on the 3 pictures here. Ionization. Ionization is very much used for the appliance we are looking at. So that means the appliances that are domestic and commercial. A number of them use ionization for detecting the flame. And what we are testing here is the signal that is given by this ionization detector to see if it could still be used with hydrogen. Maybe I can already reveal that from the testing done, and you can see on the curve on the right side, that for most of the appliances we have tested, we see that ionization is in fact not very much impacted by hydrogen. At least for the level of hydrogen we have tested, because at the end, normally coming close to 100%, the ionization will disappear. But we have been discussed yesterday, and we were told that up to 98% there is still an ionization signal. That means that this technology that is widely used will probably be very performing as well with hydrogen, despite it is not designed for that initially. Okay, now with the working method, first I'd like to say that as you know, Patrick mentioned we were in 5 labs testing. In fact, I would also like to say that there were a bit more labs testing. There was in the course of the project, Patrick has organized some meeting with external labs, and for example, A+, which is here today, have also been involved in the testing and provide us with testing results. And thanks for that as well. Thanks for that. And also some manufacturer, BDR, Electrolux, of course, that are in the project, has also been contributing with testing, and also some more manufacturer. And of course, also a big thank also for the manufacturer helping us with discussing the results and come to the right conclusion. So what we have done, that's always already explained, that we defined categories of appliances initially based on gas coil project, based on the typology of appliance and the testing standards. So we have tried to put all those appliances in boxes like that. So with the aim to try to, let's say, make a conclusion by type of technologies on the market. Of course, as you will see, there are some segments where maybe technology are too different for putting in the same box. For the method we have used, we have a lot of complex way to report the data. We have a huge Excel sheets with a lot of data. But at the end, we have been asking the labs to provide also a a card, which is a simple table like that one, where the basic results are explained. So here we call that the ID card, where you have on one side, you have the percentage of hydrogen tested. So this is the line in gray, safety assessment H2 tested. So you can see that we have tested up to 60% there. And then the different parameters that has been tested. And you see we have adopted a kind of code for expressing the result in a simple way. So a cross means that a physical test was done. And the cells were colored in green when there has been no problem, and in red if there has been a safety problem. Then we have some cells that are white. That's where there has been no test done. And sometimes we also have test colors with red color yellow color where maybe we presume there may be a problem between, maybe there is some uncertainty about the conclusion of that. Also, we have been interpolating. That means that between two cross in green, we could put it in green, because we suppose that if you test with 20% and 40% and you have positive results, then with 30% you can expect everything will be fine as well. The same kind of logic can also apply between two red cells. And at the end it ends up with some table like that. Okay, just to say before waiting, we are still in the process of working with THyGA table, so don't take all the information of THyGA table for granted at the moment. Everything will be ready in few weeks. But at the moment, we are still working on THyGA tables. There are some few inaccuracies, but the conclusion I will bring today are final. But in the detail, if there is one appliance or two having flashback, or at which level exactly, this could change a bit because we see that we have some logistic issue by making THyGA tables here. But the idea we're showing that is to say, okay, this is a kind of table that is telling you everything about a family of appliances. So you have here the different segments at the top. So for the one that are following from Teams, you have on the top part of the table, you have the appliance. So one column by appliance. You have the main feature of the appliance, so heat input, max, min. If there is a combustion control, okay, this is for the very first family, which are the fully premixed boilers. And also the category, the gas category, according to the SEN. Then the gases that we have used to mix hydrogen with. It could be EU low, that will be typically a gas we will use for when we make some adjustment. G23 possibly, or pure methane. And then you can see later on the percentage of gas, percentage of hydrogen in the gas. So from 0 to 60, and at what level of hydrogen we had detected a problem. And then you can see that the problem type will be in the list at the second part below, down in the table here, showing what kind of issue we had. So it's a bit very compiling, and maybe it doesn't tell everything, because it doesn't tell, for example, at what percentage of, if you have two red cases below, you cannot see what percentage is really the problem appeared for which problem. But at least it has a merit of bringing us a value at the end of what is the end result for a given family of appliances. And our philosophy was to say, when it is about safety, that if there is a safety issue for one of the appliances here, the conclusion we will give at the end will be based on the worst case we have been measuring. So that if only one appliance is red, the whole family will be red in our conclusion, which is a final table that you see here. For a group of appliances here, the segment 100A fully premixed boilers. So you see that is resulting, the table resulting for the big table will be that one. So this is about the methodology. Okay, and now I come to the results. And maybe I can take one of the questions from Mindert, which is online. And yeah, that's maybe I should have mentioned that what we call premix is fully premix. So it's appliance where the total volume of air and gas are mixed before it comes to the burner end. So before going to the results, again, I'd like to say that the results you're going to show, to be seen, to be presented now, are not completely final. So I will present you, go through the list of the different families, and we will maybe use a bit more time on the two first, which are the boiler fully premix and the cooker domestic. The reason for that is that those are the two segments that are covering probably 60 or 70% or maybe more of the volume of gas appliances installed in Europe. So it gives meaning to bring a bit more focus on those one. Also knowing that we have some time constraint for today, so it will be a bit difficult to go into very detail for all segments. And I think I was a bit too fast here. Yeah. So once more here, a detail of the ID card. For example, here the EN01, which is the first test done by NG, for example. This is we have a segmentation number that, according to the list that has been shown by Patrick at the beginning, max and mean. If there is a combustion, control on the appliance. And this is important because when there is a combustion control, you might not be able to do some adjustment, for example. And then the category according to EN437, and the test gases that has been used here. So this is the results for the category fully premixed boilers. And as you see, there is a lot of red here, but the red is due to the fact that we have tested those appliances with adjustment, and the red color is mostly coming from adjustment situation for those premix boilers. There is also a number of cold start. Typically, this is something that's happening at higher percentage of hydrogen, like 40%. Some case also hot start, also mostly at 40% higher range of hydrogen. And also flashback was observed, but again here for 40% or more. So the main problem is really the adjustment here. So this adjustment, so you can see that what we have measured is the CO after having adjusted the appliance to a low calorific value gas with hydrogen and test with high calorific value gas or EU high gas. Then we measure in a number of cases CO above 1000 ppm, which is with our criteria to consider we enter in a dangerous situation for the end user, as stipulated by some of the standards used for certification of appliances. But you should also note that a number of appliances that has been, let's say, we have tested for adjustment G, passed the test. That means that the situation is not necessarily a systematic situation we see for all boilers. And one of the things we have seen is that one of the boilers, in fact, equipped with a combustion control based on CO, by the way, has been able to maintain the air excess constant despite the change of gas quality after adjustment. And that means that there is no specific problem with CO on these kind of appliances. And also the other thing is to be said, and that I think Stefan later on will also insist on that, is that the appliance that where the manufacturer has stated that appliance should be adjusted on the O2 value and not the CO2 value. In this case, when we adjust on O2 value, we saw less problems and it was adjusted with CO2. In the final report, we will try to be more accurate also on the numbers and give numbers about how many appliances with such adjustment have passed the test and how many with these appliances did not pass the test and so on. So in principle, yeah, also the thing that we like to mention there is that for some cases, the manufacturer states in the instruction to installer that the appliance should not be adjusted. So in this case, we just follow the instruction. As mentioned before, we try to mimic what is done in a real situation. So in a real situation, we suppose that if an installer is getting instruction, he will just follow the instruction, and if the instructions say don't modify the adjustment because we have a combustion control that is taking care of that, so we suppose he will not do that. In some cases, we had also some appliance with adjustment controls, with combustion controls, where manufacturer also given O2 or CO2 value. In this case, we say, okay, in this case, even though maybe the manufacturer don't wish installer to do that, as there is a value here, we will simulate what's going on in case this operation is happening. So 4 of the appliances didn't pass the test, and 4 passed the test for these cases here. Just to illustrate with data here what is happening here, you can see on this graph, again, what has been shown before, but you can see on the table there what kind of measurement we have done, what are the results of the measurement you can do at EU high. You see we have a O2 value, measured O2 value of 0.4. So the normal value for this boiler will be 3.8. This is a value that is stated in the manufacturer instruction. And then, this is so we adjust, come back in here, we adjust with 3.8 for the O2 with this gas here, so low VOB plus hydrogen. And then you change the gas and go to high VOB. And then you see the O2 is 0.4%. This is very, very little. This is very close from stoichiometry, and stoichiometry, it will not burn properly. And here we measure, you can see in the table, we measure here 1000 ppm. So definitively, this is a situation that will be problematic in the future. If the installer coming to a place has no information about the presence of hydrogen, and if he does this kind of adjustment here, there is a potential danger for CO formation later on. Either we have not got any other issue there apart of the things I have already mentioned. So we have before mentioned already some flashback for but above 40%. Now we also look at the CO emission here, and you can see this is a trend we can see for many of the appliances here, and this can also be explained by what Chris has shown before. So we see that when you inject, and again here, this is really without touching anything here. So it is just to be inject hydrogen at the boiler with G20, and you increase the level of the volume of hydrogen. You don't touch anything on the boiler when doing this test. And when you do that, you can see that there is a CO decreasing, and For most of the appliances, there are few appliances where this is not true, but in the vast majority, you can see that there is a decrease of the CO. Here and in the following slides, I will show for the segment where we have a lot of appliances tested, we show two graphs because if we put all the curves on the same graph, you will not see anything anymore. So that's only for making the graph readable. But you can see that a part of two appliances on the right side, CO is generally decreasing. Then the CO at Q-min, so the first part was on the maximum load of the boiler. At a minimum load, you can see that it's very flat and also very low, by the way. The NOx emission are, in fact, following the same trend. Here you have really, I think, all of the curve are going down here. We have not a single one going up. So by injecting hydrogen in the grid without changing anything, there will be a lower level of NOx in the flue gas. And the same at Q-min, knowing that Q-min is maybe, you can say that the level of emission is lower here. So you see that we have a level of 50 here. Here it's a bit lower. And here, because of that, the curve are a bit more flat, but still a trend to decrease. The efficiency, you can see again here two graphs for the same reason as before. Slightly increasing, sometimes decreasing, but here our explanation is that because of the new gas composition, you have more latent heat that you can take from the flue gas, because we are having here to appliance our premix condensing boiler, so the condensation, we have a return temperature of 40 degrees, so you can get more condensation under two situations when you put hydrogen, and this must explain the slight increase of efficiency. And I think I just lost connection with the computer again, but this curve here about we see an increase of the efficiency. This is unique for boilers, as you can see later on. Most of the other appliances are quite flat, but the other appliances we will discuss are not condensing ones. So probably this is the right explanation for what we see here. Oh, thank you very much. Thank you. And and then there is a measurement we have done on unburned hydrocarbons, and the unburned hydrocarbons are decreasing for when you inject hydrogen. You can imagine that when you replace one component with another one, when you take some methane out of the gas, there will be a natural less methane in the flue gas as well. But the decrease is much stronger than the volume of gas that you are replacing. So that means that, in fact, we believe that here, because of the flame, the fact that you have a faster combustion with hydrogen, there are less methane escaping from the combustion room. But in the same time, you also have more emission from hydrogen as well, which is also a greenhouse gas. But the balance, okay, we have only one measurement here. I think there will be more in the report on some other appliances. But the balance, if you look at the balance between this one and this one here, you will see there is a global positive effect on green gas emission. There is a question about, I will take just question online while we're here. There is a question about the color of one of the tables showing that there was red with methane. It's not red because of methane pure testing, but it's red when we have blend hydrogen with methane. And I think we have to modify a bit the way of presenting that because it's, I think it's a bit difficult to understand, but I think in the report we will make it clear, and I think we will remove the color from the gas used to blend hydrogen with, because this is... There is a question also about the varying gas quality or setting the appliance on the field. I think this is for VP5. I will leave that question out for the moment. Okay, I will take other questions later on. Yeah, now the conclusion for the fully premixed boilers is that we believe that looking at the result, that because of the benefit, so let's say the positive result we obtain with O2, that if we, with simple mitigation, I think, for example, using O2 adjustment instead of CO2 adjustment, we believe that we can burn safely up to 20%. And even if you make dedicated adjustment, which is one of the questions here, you can burn up to 40%. And there are some operation things we have been measuring, for example, difficulties, maybe it's in start or stop, starting at appliance with 40% hydrogen, but this is more operational aspects, so it's not... And also a flashback was also observed with, but again here for higher value of H2. Also, a number of issues that has been not investigated but have not appeared to be a problem. So I can mention some of them: the flue gas length, the low temperature of the air, for example, the quick variation of Qmin and Qmax for this kind of appliance, gas pressure variation, and so on, have not shown to be a problem. Either not the variation of electric power on the appliance. Now, looking at the cooker, domestic cookers, here we have, in fact, a cooker is generally, cooking hobs and also ovens. Two kind of technologies are in the same family here. So here again, you see some red with methane. It's not because there is a problem with methane at all, but it's a problem when we test. With the test, some of the tests we have done with methane blend with hydrogen at high level. The main problem we had with the cooker here, with the cooking hobs, are flashback when we starting, for some of them starting at 30%, but most of them were also at 40%. We have also some issue with the cold start, again here with 40%, hot start as well. And also the quick variation of heat input could be a problem because there will be some flashback when also working at higher value of hydrogen. And also the pressure change could also bring an issue there. I don't recall exactly what kind of issue in this case, but you will find the detail in the report. Okay, come back to the same picture about the flashback here. One of the flashback tests we did was in fact not a flashback test, but it was a test for the efficiency. And we had made those tests with, in fact, very high value of hydrogen, 40 and 60% here. And in two cases, we had a flashback appearing only after 50%. We will normally not wait so long time for a flashback test, but because of the nature of efficiency test, you need to wait a long time to heat a pan, and that means that we discover, and this was a bit lucky. We were a bit lucky to discover that because of this long duration of the test, we saw some very late flashback appearing here after 8 minutes, but also sometimes after only something like 40 or 50 minutes. And as a result of that, at 60% at least, we destroyed a burner. And also you can see that flashback is also followed by high emission of CO, in this case here on the black curve. Oh, there is a lot of question here. I think maybe I will wait to the end to look at it. And there is also a question in Italian. This one I will definitely not answer because I will not answer it. I cannot understand it. Also, some other things we have been measuring is looking at the flame aspect. Okay, I have to hurry up a bit now. So there is a yellow flame that we have seen here for 40%, and this is also bringing some instability here. So this is obtained also with 40%. And another problem that we were not expecting is on one appliance here, on a cooking hob with a pan with cold water on it. We had some condensation at the bottom of the pot, and the water was falling back on the burner, creating some instability, extraction, and flashback. For efficiency, you can see it's very flat. NOx is decreasing slightly, sometimes increasing, but generally decreasing. CO decreasing generally, some cases increasing. So this is something we have seen. Unburned hydrocarbon, here we have a figure which is a bit more contrasted. There is, it's a different flame here. We are having a flame with only partial premixed. So let's say the thing we have seen on for the fully premixed are quite different. Also, you will find in the report some information, because in some cases we have been also measuring temperature at the level of the burners, and you will see also how this temperature can evolve. And for example, well, we were expecting the temperature increasing with hydrogen because the flame coming lower, but it's not always the case. And if you look at premix boilers, you can see that in fact the temperature may decrease because when you inject hydrogen, you have higher air excess, and then you have in fact a compensation, and that means that the temperature at the burner is decreasing and only increasing again after 40 or 50% hydrogen. I will now present shortly the other segments. So other boilers, okay, it's a bit complex to read about this, but let's say we have not big problems before 40%. The problems we have seen, some cold start, hot start, and some flashback at 40%. Basically, no big issue below 40%. Efficiency flat, NOx decreasing, CO decreasing. Same as before, a very typical pattern. Water heaters, one of the water heaters has problem with methane here. So this one, we are not going to bring it to the comparison with the other. It happened that, for a reason I cannot explain, that some of the appliances we have tested had problem with methane, and of course, we should not conclude on basis of that, because this appliance would not be passing certification normally. So I said no explanation for that, but this cannot be used for this comparison. Otherwise, water heaters, only non-premix or partial premix has been tested here. No problem at all here, as you can see. Efficiency flat, NOx flat or decreasing, CO decreasing. Catering equipment. Okay, catering equipment here, we have a catering equipment, a number of them are also fully premix, and for them also we have tested some adjustment tests, and same conclusion as before. Adjustment can bring a problem, and adjustment is a problem, and is the only problem here that we have seen on such appliances. Oops. Efficiency, okay, we have 3 efficiency here. Okay, yeah, just look at the scale. It's maybe the scale should be bigger. I'm not sure we should conclude anything about the graph on the left, but it's like that. NOx decreasing, CO decreasing, or quite flat. Space heater. We have flashback from 40%. Otherwise, basically no big issue. Efficiency constant, NOx decreasing or constant. CO, okay, here we have some slight increase of CO or increase of CO for one of the appliances. One is stable and the other one is decreasing slightly. I let you conclude yourself. Combined heat and power. So here we have 4 different technologies. We have 2 internal combustion engines. We have a microturbines, and we have 2 fuel cells, PEM and SOFC. Very surprisingly, the internal combustion engine could burn up to 40% hydrogen without problem. We were expecting a lot of issues there because of the methane number, but nothing happened there. Then we have for 1 or 2 appliances, we have to look at the detail more in the result more in detail. We have high CO, as you see here. So efficiency more or less constant. Okay, we have on this graph you have either electrical efficiency, thermal efficiency, or combined. So we will make that more clear in the final report. But basically, there is no impact of hydrogen efficiency. NOx is, well, going one way or the other, as you can see here. And CO emission, we have very high rates of CO for the SOFC. But here, it's a bit difficult to conclude when we have only 1 appliance. And this is one of the limitations of what we have done here, is when we have only 1 appliance, it's kind of difficult to make a proper conclusion. Gas heat pump, okay, only one tested here, nothing wrong has happened with that. Tested up to 40%, NOx decreasing, efficiency constant, CO decreasing. Radiant heater and commercial air heaters, everything green, nothing to say. Efficiency, okay, decreasing here, but once again, I don't know, I would be very cautious measurement about the measurement here. Maybe we will elaborate a bit more in the report. NOx decreasing or slightly constant or slightly increasing. Yeah, you can see the results here. So it's quite the same as most of the other segments. And then Henri, my colleague from GC, will present the long-term test. Sorry.
Hi, I'm Henrik Kini, so I'll talk about the long-term tests that were done. The objective of this test was to see the effects long-term running would have on the appliance using a blend of 30% hydrogen and natural gas. So the possible alteration were monitored by measurements in the flue gas of the different appliances. And then the appliances were dismantled at the start of the test and at the end to be able to compare every piece of equipment and see how the wear and tear happened and if anything specific happened. And yes, so the idea of the test was to do an intense test on a short period that was about 6 months long to have an idea on how it would affect on a couple of years of usage. Yes, so this is the timeline. It ended up being a few months later, but it was a total of 6 months testing around. And here we have the experimental setup with, for the cookers and the boilers. We see how the pros were set up, the flue pipes with the pros going in as well. And so the data was very good because, well, nothing changed. So there was no impact from the blend on the performances of the appliances long term. And on the wear and tear side, neither. It's what you would expect from a regular working of the appliance with just natural gas. So this is a normal amount of deposits, and this is, well, same, a bit of discoloration, but it's normal, so nothing specific. So the conclusions are quite quick. So in total, there were 2 cookers and 3 boilers that were tested by DGC and 2 boilers that were tested by the GVI. The cookers were tested for more than 2,500 hours and the boilers for more than 3,000 hours, so which is equivalent to about 2 or 3 years of normal usage. All emissions and efficiency levels ended up staying the same, and normal signs of wear and tear and of deposit appeared. So in conclusion, we noticed that 30% hydrogen did not affect the well-being of the appliance during those long-term tests. And yes. So now back to Jean for the conclusions of the VP3.
Thank you, Henri. Okay, I will be a bit fast for the conclusion. Okay, that's a picture that we know today. It might be a bit different, very small variation maybe after we have processed the last result, and I think we're also waiting one test report still, so I think we definitely will not change the picture there, but we will maybe make some fine adjustment there. But basically the main message is that you see here, if you are making a sample mitigation, adopt sample mitigation like O2 adjustment for the fully premixed appliances, 20% should not be a problem. Then when you go over, if you want to go to 30%, certainly you need to look more in detail about how you can mitigate this problem of field adjustment. And there are some solutions, and I think there are a lot of questions in the chat about that. I think maybe we can keep those questions about how to solve the adjustment problem to the VP5, because there will be a presentation on that, and there are some ideas brought there. But definitively 20% seems to be, at least from what we have done here, so with a limitation that you know about the number of appliances tested, and you have to remember that we have 200 million of appliances installed, and to be conclusive on the very one is impossible. So, but we have tested almost 100 appliances. So this is the best we can do with a given condition of the work we have been given here. But from what we can see, that 20% seems quite realistic, but going up to 30 would need to have a discussion about the mitigation. And also, I would say, in any case, going up to 20 would require to discuss mitigation for the adjustment. Here, what's quite so. If you dream to go to 50%, I would say this is, as we see, you have understood that there has been already a lot of issue with flashback, cold start, hot start, or other problems. Probably this is not going to happen with the park of existing appliances. So from the survey at the beginning, there were some people believe that there will be 40% in the grid or 50%. I don't think this will happen with the park of appliances that are already there. It cannot, maybe it will happen with new appliances that are designed for that. But the appliances that are already installed, personally, okay, this is my point of view, but from that slide here, you see it seems reasonable to stop at 20, or it's a very extreme case at 30 if you really want to have 30, but then you will need to do a lot of effort to guarantee that there will be no safety issue for the end user. Otherwise, we have seen that there are a lot of points for which we were not very sure about what will happen, and for which we didn't find really issue with hydrogen. Like, for example, the flame surveillance, for example, is going well with ionization. We don't see problem with low air temperature or very long flue pipes. We don't see big issue for the rock, for the plug flow. The problem we had with the plug flow, we have some case where we had problem, but we have tested plug flow with 40% hydrogen. And most of the problem are probably due to the high level of hydrogen and not very much of the plug flow itself. The delayed ignition, from what we have seen, is not really problematic. And if you look at the impact on performances, you can see that efficiency has no impact or a slightly positive impact on fully premixed appliance. And decrease of CO For some segments, you might say we don't have enough data to be really conclusive. So that's where we have written unclear. For the methane emission, at the moment I left it empty, but we will write something in the final report when we have processed all the data. And maybe a last thing that was mentioned also by Chris is that for when we look at think about operation and service to the customer, clearly if you have with hydrogen you will have less heat input, and that means for cooking or water heating, there might be a comfort issue to the end user. Maybe the shower will be a bit colder compared to the temperature that the user is used to. Okay, we have not quantified that, but that's and the cooking time may be a bit slightly longer as well. Probably not very important problems, but still I think we have to look at segment by segment to see if this could be a problem as well. And this is it. Maybe shall I take some question? Maybe I think there is a question. There are many questions, so I cannot answer to them. So you just stop me when I don't have more time. I think we have 5 minutes or something like that. Okay, there is a problem. No, sorry. There is a question about the unit used for CO. We use ppm. It's dry air free, so it's stoichiometric CO. So we could have used milligram per kilowatt hours as well, but the ppm is corrected from air excess. Yeah, there is a question about the NOx and the flame temperature, and this is typically that's something you read if you read about hydrogen and flame temperature. You can read that hydrogen is increasing the flame temperature. But remember that what the exercise we are doing here, we are let's say mimicking what is going on in a real situation. That means that we are not changing the anything on the appliance when we inject hydrogen. And that means when you put hydrogen, then you typically have too much air for compared to the nominal combustion. And because of you have more air, you will decrease the flame temperature as well. So in a way, you have a double, let's say, a conflicting or two phenomena that are in a way going in different ways. The hydrogen is going to increase the temperature, but the air excess is going to decrease it. And from what we can see here, and the NOx decreasing, is because the air excess is bringing back, in fact, the temperature to a lower level that it would be with pure methane. So if you have now done the test where you adjusted the air excess at the nominal value with hydrogen, you will probably see a higher flame temperature and higher NOx. And I think this is typically the case for industrial burner. When you have an industrial burner, then you will adjust to a constant air excess. And then when you have hydrogen, you will have typically a higher flame temperature and higher NOx. I don't know if we have to... I don't know. The plug flow. Okay, plug flow. Plug flow is a situation where, I think I mentioned that, is where you have a gas in the grid and suddenly you inject hydrogen. So you have a kind of volume of gas that is going to the end user that is composed of, for example, typically methane and just, or with some few other components. And in few seconds you will have another gas. And plug flow was to test if what had happened in this situation. But I think maybe we should treat the other question later on to respect the, yeah. Okay, thanks for your attention then.
So thank you everyone. We'll have a coffee break now, so you can go outside. There should be some refreshments available, and we are back at 11:40 for the rest of the session. Thank you.
is Lisa Blanchard from the CEA. So, wrong. What I'm going to present is experimental results that are slightly different from what was presented so far because it's not related with combustion. The objective of those tests was to evaluate the tightness of component of the gas distribution network from the gas meter to the end user in hydrogen plus methane mixture. And so to do that, the components were gathered from Germany, Denmark, Belgium, and France. As Jean said before, the philosophy of THyGA was to test as close as possible from the operation conditions. So the pressure that we used was 35 millibars. And we compare our result to admissible standard leakage rate. So 1 liter per hour and a more conservative one linked with appliances, which is 0.1 liter per hour. So before I start to jump into our experimental method and results, I just would like to present you 2 projects that are supporting our results. So there is the High Delta, which is another European project, and one of the objectives of this work was to evaluate if we will need specific tightness requirements for 100% hydrogen compared to the ones that are currently existing for natural gas. So to do that, they created control leak in a specific junction and tested them in N2 natural gas, 100% hydrogen at different pressure. And there is this also Ukrainian consortium that tested the tightness of 5 entire gas distribution network at a full scale. And here again, they did this test at a different pressure. So the main conclusion of those 2 projects that are related to ours was that, unfortunately, at those low pressure, the test could be give a little bit inaccurate results. And also the temperature would have a strong influence. So now we go to our experimental procedure. So we gather all the components from those different countries and we created 10, by joining them, we created 10 lines of gas to be tested and we perform on them a pressure drop test. So we have the short-term test and the long-term test. So so we fill the line at 35 millibars in 3 different gases were tested, and after 15 minutes of stabilization of the gas in the line, we monitor the pressure drop, or the pressure, as well as the temperature. So in the image, you can see an example of end of a line with the pressure gauge and the thermocouple to monitor the temperature. So I'll just show you the different lines that we have been tested. What is important to see here is that there is a lot of different coupling, different joint, different material, valve, gas meter, etc. All of them were clean before joined. And they were actually joined by an installer from ENGIE. And here are the 6-10 line that we've tested. So here you have the results of the short-term test and the leakage flow in liter per hours for helium, air, and methane and hydrogen blend. What we observe generally is that there is not, at those very low pressure, not so much difference between the 3 gases. And also we are generally much lower than the admissible standard leakage rate. yeah, so that's the main finding that we found. And so now we are moving to the long-term test results. So I didn't want to overwhelm you with a lot of curve. So I just show you an example of what we've done here. So for one line, we have measured the pressure drop. This is the dark line here, and the temperature. And then we calculated this pressure evolution, which is the pressure that would only evolve according to the temperature. So if we look at the difference between the yellow and the dark line, we can see that this drop is definitely due to a leak. So we did that for the 10 lines, and some of them could hold the pressure for more than 100 hours, and some of them couldn't. Right, sorry about that. What is important in here is the pressure drop in liter per hour that was measured at the end. And generally, despite the drop that we saw here, none of the lines show leakage rate that was superior to the admissible standard rate that is current for the natural gas one, right? All right, so that was the main finding for the long-term test. Right, and so the main conclusion for this part on the tightness. So at those low pressure, we couldn't see any difference between air, helium, and the H2 natural gas blend. So from that, we can say that if there is no leak in natural gas or in air, we expected that there would be no leak in hydrogen. This was supported by the European High Delta project as well. Then after more than 200 hours, we couldn't see any deterioration of the component or loss of tightness. And yeah, generally, as I said before, the pressure drop that we measured for short-term or long-term tests were not above the current admissible leakage rate. Right. So I'm now gonna give the floor to Stéphane.
So to do that, we did a post-processing of THyGA's test on on some selected boilers. And from the results, we calculated the percentage of water in the flue gases from the air excess and from the fuel on the flue gas composition, and which enabled us to calculate the dew point in the flue gas, and we compared that value to the temperature we have measured in the flue gases. So one of the first thing we have looked at is the percentage of water in the flue gases, and usually from the measurement we can say that the percentage of water in the flue gases decreases with the increasing proportion of hydrogen, and this is caused by the increase of the air excess. It's just like NOx for the NOx, which are decreasing where we expect it to increase. We have a decrease of the percentage of water because of this increase of air excess, which has a strong impact on all combustion and flue gases composition. And so what happens to the condensation at Qmax? We have compared, I compare here the temperature of the flue gases measured from the THyGA project to the dew point temperature calculated from the percentage of water in flue gases. And so what we see is that at the maximum heating power, there is absolutely no problem, because for the worst case, the difference of temperature between flue gases and dew point temperatures is 50 degrees. So no risk at Qmax. At the minimum heating power, the difference is not so high; it's just 25 degrees. But when you look at what's interesting for us in the future, I think, which is the 0 to 20%, you can see that there is not much difference either on the one side on the flue gases temperature, and on the other side on the dew point temperature. So there should be no problems with the introduction of hydrogen concerning this extra condensation, even at the minimum heating power. If there is a problem, there might be a solution to mitigate condensation problems, is to increase the heating power at the minimum heating power, in order to have a higher temperature of the flue gases. One other question we were asked is about natural drought. The question was, if we add hydrogen, if we change the gas composition, what will happen to the natural drought? Will it be still okay, or does hydrogen addition could cause problems? And for that, we have taken into account two phenomena. The first one is the buoyancy. We have compared the density of the flue gases to the density of air, and if the density of the flue gases is much lower than the density of air, of course the gas can go up. If it's the contrary, we have a problem, because natural draft is blocked. And the other phenomenon we have looked on is the flue gases flow rate. Because if there is a decrease of the of the flue gases flow rate, there will be a priori no problems. But if there is an increase of the flue gases flow rate, it will require more investigations. And so what we have done here is also post-processing of the measurement of the THyGA project. We have used on the boiler inlet the gas flow rate and its composition. On the outlet, we have used the temperature of the flue gases and the proportion of CO2 and oxygen. And from that, we were able to calculate the air-fuel equivalence ratio, the weight flue gas composition, and then the flue gases flow rate and the relative density of the flue gases compared to the air. So first, the flow rate. As you can see on the figures, flow rates are most of the time decreasing or remain constant. So it won't be there is no problem expected with this phenomenon. So the next one is the buoyancy. So here we have a comparison of the density of the flue gases to the density of air at 15 degrees. And it's a relative density. So if the density is lower than 1, then you will have natural growth. And what we can see is that the addition of hydrogen does not change much the relative density of the flue gases compared to the air. So at the also it's a very the values of the relative density are quite low compared to quite low compared to 1. So at the maximum heating power, no problem is expected. At the minimum heating power, the relative density is higher, but still lower than 1. And also on the range of 0 to 20% hydrogen, we don't see much changing of the relative density, so no problems are expected on this hydrogen concentration range. And this was for with considering air at 15 degrees. Now we have also considered the really worst case when you want to operate your boiler with an outside air temperature of about 35 degrees. Of course, you don't want to heat your home when you do that. You just want to have some hot water to clean the dishes, for example. But we wanted to see what happens in that conditions. And in that conditions, we still have a relative density of the flue gases, which is lower than 0.9. So natural gas is still effective. Yeah, so we consider that even in this condition, no problems are expected compared to what happens with natural gas or methane. So other conclusion for natural growth, I guess make sure with 20% hydrogen has a very low impact on natural draft. In most cases, the flow rate of the flue gases remains constant or decreases, so flow rate is not an issue. The problem could occur at the minimum heating power. Well, no, the worst case is the minimum heating power, but even in that case, from in the range 0 to 20%, there is not much change of the relative density. There is also a difference which is high, which does not vary much between the flue gas temperature on the dew point temperature. So no problem are expected also. Yeah. Now, as Jean has told you before, adjustment has been identified as the big problem of gas appliances already installed in the field. And the higher problem, the worst condition we have encountered in the project is adjustment. An appliance adjusted at the HLO plus 20% hydrogen, which is the lowest VOB index, and used that with a EU high, which is the higher VOB index of the diluted gas in Europe. And this causes problem because of two reasons. The first one is the VOB index jump, which is quite high compared to what is used in certification, for example. For the test, the VOB index jump is over 7 megajoule per cubic meter. While when you perform tests with limit gases during certification, you use G20 as a reference gas, and so also for adjustment of your appliance. and then you use a G21 or G23 for your test, which are just 4 megajoule per cubic meters or 5 megajoule per cubic meters from G20. So the VORB index jump is lower when you perform certification, and this is one of the reasons of the high CO emissions during our adjustment test, is because it's a very difficult test to pass. And the second reason why we had so high CO emissions is that we performed adjustment based on CO2, like business as usual on the field. And this is the wrong approach for hydrogen, because what you want is a certain amount of hydrogen in your flue gases, so that if the gas composition varies, you are still on the safe side compared to carbon monoxide emissions. And what we see on the, I'm sorry, I like to put some mathematical formulas on my slides. And this one shows that between the CO2 values of the flue gases and the O2 value, there is one value related to the gas composition, which is the maximum CO2 you can produce during combustion, stoichiometric combustion. And this value is quite constant for natural gases. But when you add 20% hydrogen, it drops from 0.12 to 0.11. And then what you see on the right side of the table at the bottom of the picture is that when you in that case, if you perform the adjustment with CO2 with the CO2 value recommended by the manufacturer, you will have a lower air excess when you adjust your appliance, which you don't have if you adjust your appliance with O2, because you will have the lambda you want. So what you have to memorize is that if you adjust your appliance with CO2 in the presence of hydrogen, you will have a richer mixture in your gas appliance. So I don't know if you see my my mouse. There is on the picture on the left, there is well, it's this picture shows the oxygen in the flue gas, the CO dry air free in the flue gases according to the percentage of O2 in the flue gases. The blue square is the adjustment on G20, which is the default adjustment of the boiler. And then if you adjust the boiler with at U low with the carbon dioxide, sorry, based on carbon dioxide value, you adjust your boiler with on the position of the big black triangle on the left of the manufacturer's range of adjustment. And from that value of U low plus 20% hydrogen, when you switch to U high, you go to the highest CO emission on the left. You go toward the stoichiometry, and you don't have enough reserve of air to do that without emitting so much CO. On the contrary, if you perform the adjustment on O2, you're still within the manufacturer's range of adjustment. This is the big square, the big red circle in the adjustment. And then if you switch to U high, you decrease the percentage of oxygen in the same proportion, but as you have a linear mixture, you emit less carbon monoxide. And these are the two reasons why we had in WP3 high CO emissions. Adjustment which led to percentage of oxygen outside the manufacturer's range, and a big jump of VOBI index. I won't detail all the data on these tables, but we have tested the method on several boilers. What we should memorize is that at maximum heating power, the O2 adjustment decreases highly the CO emissions when the gas composition, when the VOB index of the gas increases up to a U high. Same for NOxes and maximum heating power. The adjustment of O2 decreases NOx emissions. The situation is a little bit different at the minimum heating power, where you can see that sometimes the CO goes up or down depending on the gas appliance, but we stay minimal in CO and NOx emissions, and there is no such big increase like at maximum heating power. So pollutant emissions are kept under control at Qmin, and highly decreased at Qmax. Another solution to decrease pollutant emissions with adjustment is combustion control. And here I present some results of tests we have performed on a boiler which has a CO sensor in the flue gases. And you have a comparison of what happens if you adjust the boiler, this boiler on U low plus 20% hydrogen, you don't touch anything, you stay in that condition. Well, it's like a manual adjustment. And this adjustment is compared to the auto adjustment performed by the boiler. And as you can see, at the maximum heating power, like previously, you have a high decrease of carbon monoxide and NOx emissions. And at the minimum heating power, you have low emissions anyway, so there is no problem to be solved. We had a limited time in the THyGA project. We didn't have time to explore all mitigation solutions. Several options were proposed to us during the project, and they are summed up here. For example, there are alternative methods if you don't have an O2 analyzer at hand, or if you have maybe, if you can have the information about the percentage of hydrogen in the gas, you may have other solution to adjustment. The first solution would be, of course, to forbid adjustment. This is based on the results of both on the gas coil and the THyGA project, where non-adjusted boilers tend to behave well for all test gases we have used. While if they were adjusted to the wrong gas, they tend to produce high pollutant emissions. Another suggestion that was introduced to us was to perform an adjustment if you want to inject to make 20% hydrogen to the current gas. The idea was to perform a factory adjustment to J20 plus 10% hydrogen. Well, this is a bad idea because it leads to a richer combustion and then to higher CO, NOx, and flame velocities, which go in the wrong direction. Also, it was suggested that if there is a way to have the percentage of hydrogen in the fuel gas, then we should update the O2 adjustment according to the known value of hydrogen. So you can you can be still in the manufacturer's range when you perform the adjustment. Another solution proposed to us was to limit the WOB index range of delivered gases. This is quite difficult currently in the context of the Ukraine wars, because we have highly increased the importations of liquefied natural gas, which has a high VOB index, and we also have to deal with energy transition, and we have more and more biomethane on the network, which has a very low VOB index. So currently it is difficult to think about decreasing the VOB index range. However, in the far future, if there will be more and more places where there will be only biomethane, where you can add hydrogen. And so in that case, you strongly limit the VOB range of the delivered gas, and that could be the good solution to develop some kind of a local network with biomethane and hydrogen to limit the VOB index range. And also to mitigate this term of the impact of adjustment, it is really to use a boiler with auto adjustment. Those with ionization probe do not see hydrogen. So, but they can compensate the VOB index fluctuation of natural gas. And so, in a certain way, for natural gas, they behave like auto-adjusting boilers. For hydrogen, they behave like normal boilers, and both combined brings low emission and safe behavior, and also safe behavior concerning the flashback, because the lambda the axis increases with hydrogen, so it compensates the increase of flame velocity. The auto adjustment with a CO sensor, as you have seen, brings low pollutant emissions compared to CO2 adjustment. We found no flashback during test, but we have still some data to process, and maybe some more tests should be required in another project to go further with that sensor in order to check the advantages and disadvantages of it. And also there is one last category which is not used usually in the domestic boilers is O2 sensor. It is to adjust the air fuel ratio. It is used in the industry, and yeah, why not using it in other kind of gas appliances. Now I will talk about gas conversion strategies. Because what will happen in the future is that we will want to introduce hydrogen in gas network, while all appliances will not be certified for hydrogen natural gas mixtures. And so we need to find a solution to begin to think about a solution. What we could do is to wait until all the appliances are hydrogen ready, which is far too long. We will have to wait far too long due to the lifetime of gas appliances. We could choose to replace all non-hydrogen ready appliances. This would be costly. Or to check the compatibility of all non-hydrogen ready gas appliances, which is also very costly. So an alternative solution must be found to enable to inject that hydrogen in a gas network without changing everything. And one of the approach for that is first to establish a dialogue between gas operators and appliance manufacturer in order to check which appliances are compatible to what level of hydrogen and which are not. And this kind of approach was already done in several L to H conversion projects, country by country, where we did establish a database of gas appliances which were able to work with both gases and with well with H gases at no, with L gases at 20 millibarrels in the transition period. So I think this could be possible in the future. So gas operator will have to tell how much hydrogen at max they want in their network, and manufacturer will tell which appliances can operate with hydrogen, which can't, and in the end, there will be also appliances for which more investigation are required. And then the idea afterwards is to build a common database appliances compatibility, if possible, European. However, even with that, some appliances won't be on the list. Some old appliances, some appliances for which the manufacturer has disappeared, have lost tracks of the appliances. So one question we asked in the project, can a safety check solve the problem for those appliances? And the idea of the safety check was firstly introduced in the HyDeplo project in the UK. We have some information that is also, well, this safety check was done for all appliances during the HyDeploy project. We have heard also that it is used in a German hydrogen injection project, but it was used only on some appliances, not all appliances. And this is very important because what we have seen and during the THyGA project also is an evolution of the test of the during the demonstration project, where you have all safety measure at the beginning, all instrumentation, all lots of measurements for all appliances at the beginning, then for some appliances afterwards, and so on. So the hydrogen community is building some kind of experience around this demonstration project, and this is very interesting. And during the HyDeplo project, what they did during the safety check is they checked the proper operation of the safety of the gas appliances on the network, so it is already safe with the current gas. They perform a test with a reference gas and then test with two different hydrogen natural gas mixture in order to ensure that all appliances work perfectly well. And then afterward, for more safety, they install a CO detector inside the home. So for the to establish a safety check, first the risk when were listed. The risk identified were gas leakage, CO emissions, malfunction due inadequate adjustment, also flashback, delayed ignition, and material compatibility. I think I will accelerate if I want to finish in time. So the gas leakage rate, I think there is no significant risk increase of H2NG compared to natural gas, especially if we stay under 20%. But I think also that a safety check can be done without this kind of verification. So what can be done to check this the gas leakage of both appliances on gas network is to check sorry, the pressure drop of the gas network, or another solution is to use the non-rotation of the gas flow meter. If you shut down all appliances and the flow meter does not rotate, you don't have any leakage. But in the literature, a different value of the tolerated flow rate has been mentioned, and so I think country by country, this is something that will need to be established country by country. We have different limits, either for appliance or gas network countries. So there is not a unique value that that comes up when you perform the literature review of leakages. And also at the beginning of the safety check, it will require that all the appliances are clean. In the Gaspal project, they had this interesting curve showing the impact of cleaning a gas appliance on the CO emissions according to the VOB index range. So if you have a clean appliance, it will digest more easily a wide VOB index of gases. And then it should be checked that the appliances are maintained and maybe using the certificate of maintenance. And now we enter the difficult part of a safety check. What we wanted to do in the THyGA project is to say, hey, yeah, okay, we need to perform a safety check on some appliances, but what will be the problems encountered? The first one is to choose the right limit gases, and how to bring them to the appliance. The first one is the G20. I think because it should be used to check the proper operation of gas appliances, and also, if required, to perform an adjustment of appliances to this reference gas in order to avoid problem of adjustment in the future. The second gas is the limit gas, to check there is no flashback and there is a proper operation of the appliance. I did put as an example the G22 because I think it requires a gas with more hydrogen than what will be delivered by the gas distributor, because this safety check won't last forever. And we have seen in the project that you can flashback will occur after 1 hour on some appliances. So as we don't have the time to put the appliance in temperature, we need a gas with more hydrogen in order to compensate and to have higher safety limits. And but talking about the gases, the best way to plug them to the appliances is either at the flow meter or directly on the appliances. If you just have one cooker, for example, it might be more interesting to plug the gas to directly cylinder to appliance. And the problem if you bring bottles on the side is the capacity of the bottle and the weight of the bottle, and you have to optimize that because sometimes it's not so easy to access gas flow meters. And also during the test, you will have to the technician will have to detect flashback, which is not so easy. At the beginning, you will hear a bang, loud. More or less loud, so you have to stay alert on the side of the appliance, and visually you have a change of the flame. The flame will be brighter with proper combustion than with flashback. But you have to be trained, I think, to detect a flame with flashback, which is a flame without the premix core at the inside. And we have established a list of what should be checked during the safety check, and try to determine also the time required to perform that. And in the end, we ended up with for a home with a gas cooker and a boiler. We ended up with a test of a check of 2 hours, over about 2 hours. A little bit more if problems are encountered, like some leakages, and if you want to know where it has come from, and boiler adjustment also. This is purely theoretical. One of the partners has performed some tests to check the duration. I didn't have any time to post-treat that data, but it will be in the final report. So the main conclusion of this task is that really more investigation are needed in order to facilitate the arrival of natural gas, hydrogen natural gas mixture in the networks, in order to reduce, well, to increase the number of appliances that we know that will work with hydrogen, to build a database. So we can check in home which appliances are compatible or not compatible, build some experience together for natural gas to hydrogen natural gas combustion. And then all that in order to minimize the number of safety checks to be performed, because it will be long, about 2 hours, maybe more. It will be difficult because it requires to take some bottle gas and to plug them to the domestic gas network. And it may not be possible to bring some bottles for big boilers, for collective boilers, for example. So another method should be found. Thank you for your attention. I don't know if we have time for questions. I was long, I'm afraid.
Okay, so we're actually quite good in the timing. So we are reaching the last part of the workshop today. So I just have a few slides. I promise it will not be long, because you got a lot of information to process. Maybe it was too much, but it shows also the complexity to summarize the amount of data we had, and also the world different kinds of results we have. But it was important to have a global overview of what has been done in the different work packages, so you get a push to look into the reports and go download them, sorry, to read and see answers to most of your questions. So I just have 3 slides for the conclusions, and it will be quite fast. But first, before going into the details of the conclusions, I wanted to thank all the partners, and especially the speakers today, for this presentation. It was not easy feat to gather all the information in a few hours. And also, thanks a lot for our manufacturer partners, BDR Thermea and Electrolux, which provided very relevant views on the conclusions, so to make sure that what we are showing today makes sense for the industry. So it was important to have this peer review yesterday. We had very interesting discussion, and I think it reflects in the conclusions that are to come. Okay, first conclusions are quite technical. Gas is an energy vector we deem needed for the energy transition to reach carbon neutrality. So in that sense, it really makes sense to explore any pathways possible to decarbonize, and blending is an option. Okay, there are different strategies, different opinions about that, but still it's always worth digging into the technical aspects to explore it, understand the complexity of these options. So it really makes sense to have a project such as THyGA to dive into the impact on end use, to understand exactly what we are talking about, what will be the impact, and the complication to implement on the field. I think the main strength of the project is that we had a very extensive test campaign. That's something that has not been done in other projects we know about, not only because of the amount of appliances we tested, around 100, but also because we tested a great variety of systems to have generic conclusions. Sometimes we don't have many appliances for CHP, for gas heat pumps, for example, so it's complicated to draw conclusions, but still it gives insights on these appliances categories. And that's important to not have alone categories of appliances without having a look. Because what happens in the end, the problem will not be about the mass sold appliances. It will be about these lone appliances which do not have any manufacturer today on the market, or which have not been tested. And so having a lot of different test results is very important to give a global view on what are the impacts and what we can expect. So even with our extensive test campaign, we are touching only a small amount of what is being installed or being sold. So as Stefan said, sometimes we may have to implement other strategies like safety check, even if we have to avoid that. And one way to avoid that is to discuss between member states, DSOs, gas providers, to try to improve knowledge sharing and try to minimize the different and the additional implementation on the field. Today you only saw one fraction of the results we have. Of course, it was a very great challenge to summarize everything in tables that were not easy to read. But you will see in the reports that there are many more information, many more analysis, many more things to look into. So I really encourage you to have a look, to read that, eventually come back to us with questions. The THyGA project has an official end by the end of the month, but the partners are still on the market. And we'll be glad to provide information, insight, to support the manufacturers, the associations, and the same technical committees. So this is really not the end for us, and please feel free to contact us. Our conclusions are that blending up to 20% is technically feasible. We saw that there could be some limitation to adjustment, but still, really the core of what is needed for implementation is that it's not only a technical feasibility, but a collaboration, a strong push of the industry, DSOs, manufacturers, member states is needed to go further and not stop at a lab test. To implement blends on the field, we have different aspects to address, and they cannot be taken care of by ourselves as research labs. Mainly, we have to talk about liability and adjustment. So liability, we showed in the project that the majority of installed appliances technically cope with 20% of hydrogen in natural gas for end use, but there are liability issues with that. As Chris explained before, in reference to the gas appliance regulation, existing appliances do not have to be designed for use with blends. So H2 and natural gas blend is not considered as normal use, and therefore manufacturers are not liable for any negative impact caused by blends on the field for existing installed appliances. So it means that member states have to define a methodology to deal with that, to give an agreement for existing appliances to be fed with blends of hydrogen or natural gas. This is done nationally. Generally, each member state, each country has its own methodology, its own consultation approach, and is addressing the topic. For example, last year we know that France and Italy agreed on their local territory to blend up to 2% of hydrogen. That's the first step. Then we have to going on with consultation to go higher. But this is something very national. And we think that if we want to go further, to go at a higher pace, we need to harmonize the methodology used from one country to another, because the knowledge necessary for each of the countries to authorize these blends could be used by the others, because there is a certain methodology, there is some knowledge gathered, there is some conclusions made or risk identified. So really, our recommendation for that, to really push forward blends from 0 to 20% or even higher, if we wish so, is to favor knowledge sharing between member states and gather all the stakeholders, not only one type of appliance manufacturers, but really all associations, representatives, all gas distributors, all safety authorities, to discuss how blends of hydrogen and natural gas should be dealt with for existing appliances. And for us, it's very important because that's a starting point to go further in terms of injecting hydrogen in the natural gas grid. Second point, adjustment. Okay, we discussed it a little bit today. That's a topic. That's actually the main topic we see with fully premixed appliances like boilers or catering equipment. And we also saw in the Work Package 5 that there are some simple ways to deal with that. It's a very simple mitigation sometimes to come back into safe operation with appliances that can be adjusted. But it's important to consider it. And also we have to keep in mind that this methodology we propose, like O2 adjustment or to forbid adjustment out of the manufacturer's settings, also can come into, cannot comply with other national or local regulations that could be implemented. So it's very important also to have a global view on what it means for adjustment from a technical point of view for an appliance, but also for the rules in a country or a region. So that's why our second recommendation will be really to encourage also the discussion around this practice of adjustment. Today we have different practices from one country to another. Maybe it should be the case tomorrow. It's not an obligation to harmonize everything, but the trends and the options could be discussed with all manufacturers, all associations, and the ESOs to try to harmonize that. At least share knowledge, share the options, and understand why one country does one or the other. So really, we think that it can be addressed, but it needs to be discussed. And that's the next step for blends from our point of view. And I will leave the floor to Alexandra for the final steps.
We don't have questions online, I think, but if there are questions and we have a bit of time.
Yeah, sure.
So if there are any questions in the room, for Patrick.
Or the others also. Share questions.
Before we do, I'm just going to stop. No questions. Okay, that's fine. In that case, sorry, to me.
Thanks.
So thanks a lot, Patrick. Final steps of the project. So as was said already, the project is officially closing end of March, although we will still be working on some documents as well in April. But the results of the project will, of course, live on after that. And this is just to give a little overview. We with all the partners and ourselves at the European Gas Research Group have worked during 3 years to make sure that the results of the project have a good communication, dissemination, and in the future exploitation. So the THyGA project was a really nice project to work on, and we've had a lot of interest and have managed to produce a lot of interesting events. So I think in total, THyGA partners presented the project in some form or other in over 40 different events, including some major international conferences, the IGRC, the World Gas Conference, At the World Gas Conference 2022, the THyGA project was selected as an Innovation Award winner for the category utilization. So we were quite happy for the recognition. So that was an industry choice. There was a lot of different papers published. So here we see one in the journal Energies that was also well received and downloaded many times. In terms of the project internally organized 4 major workshops, such as this one, but also participated to a lot of smaller events that we organized for the members of the project and also for different audiences, together with the CEN technical committees, together with manufacturers, representatives, and also in collaboration with other close projects inside the Clean Hydrogen Partnership. So we produced a lot of materials. All of this is most of this is available on the THyGA website, so I really encourage you to go and have a look. We have different information about news, about publications, which are the deliverables of the project, and we are also going to have open data publications that are going to go on the website, such as the project test protocol, the reporting test sheet, the aggregated test results, and the roadmap tool. So these are public deliverables that are coming at the end of the project, of course, summarizing all the work that has been done so far. So they are not, some of them are not published yet, so 6 will come early April. So the project team is working on finaling those at the moment. So we encourage you to come back, and we will communicate those results when they are available as well to this group who registered for the workshop. So we hope that will be useful for you. The THyGA results will also be disseminated to various groups that were partners during the project, such as the CEN technical committees, and the members will support presentations in technical meetings as needed. So the THyGA website is here on the slide. It's THyGA/project.eu, where you can find all the public information. There's also a LinkedIn page if you want to follow that. That can be a nice way to get notified of new information. And the contact email for the project is this one. So it's contact THyGA@ng.com. So thank you very much to everyone, to the project team for the really nice collaboration, to the Clean Hydrogen Partnership and the European Commission for the support during the length of the project, the advisory panel, the manufacturers, and so the THyGA project is not completely finished. We are still working on it, and when it is, the THyGA team will still be around and continue supporting the dissemination of those results further. Thank you very much. So I think we still have a little bit of time. If there are new questions, we could take them. Let me know. I don't know if we have questions online. Can you have a look? 1 second, sorry. No. Okay, no new questions. So thank you very much then to everyone who attended online as well. The meeting was recorded, so the recording will be shared when we had time to process it, as well as the information that you saw on the slide. So that will be shared with you by email later. And the questions, thank you everyone who asked questions. We answered what we could for all the speakers, and they will be compiled in a written document that will be also communicated to everyone who registered for this event. If we're, Patrick, I don't know if you want to say closing words. Otherwise we'll just want to mention there's going to be a picture.
I don't have words, but just once again to thank everybody, because it was very important for us to get support from the industry in this project, especially manufacturers, associations, and technical committees, because this kind of project is, the goal is to publish as many things as possible, to have data used by the industry, and I think that's what is being done, and that's very important for us. That's really was the target from the beginning, so we were very glad to have so much support from the start, and We hope you didn't wait too much, but things are not being published, so please feel free to contact us to get more input, more dedicated presentation. We'll be there to disseminate the results we make. And thank you very much again.
So thank you very much for everyone online. We will be closing the live stream now. And for everyone in the room, we wanted to have a quick picture for us, also for the project, as a memento. So thank you, everyone. This is, again, the THyGA credentials. There we go.